Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tare, and I haven't made a calculus video in a while. I'm almost done with my series on first year calculus. I think the last thing I want to talk about is Taylor's series, and actually, I think I'm going to do one more video after this one. I'll do a derivation of Euler's formula, which is one of the most important formulas in mathematics, which we can easily derive from the Taylor series of sine and cosine, as well as e to the x. Anyway, let's begin. So, what is a Taylor series? Well, uh, suppose we have a nicely behaved univariate function f of x. And when I say nicely behaved, there's a more technical word called analytic. And all analytic really means is that it's infinitely differentiable. That means that at least for some domain of f, or subdomain, you can calculate as many derivatives as you want at any point in the subdomain. So if that's the case, then suppose you have some value x equals a in the domain that you want to approximate f at that point. Well, the way you do it is you use this thing called the Taylor series. And Taylor series are really nice. So here's what it looks like. If suppose you have this function f of x and you want to expand it as a series of powers of x minus a, where a is the point you're expanding about. So if x is close to a, then x minus a is small, and x minus a squared is even smaller, and x minus a cubed is even smaller than that, and so on. So then you get these coefficients in front, which I'm calling CNs. You have the form of the Taylor expansion is f of x equals this infinite sum. This is summation notation, which I'm pretty sure most of you've seen. It's a sum as n goes from 0 to infinity of Cn times x minus a to the nth power. And if you can write that out term by term if you like. It just looks like C0, that's a constant term, plus C1 times x minus a plus C2 times x minus a quantity squared, and you can keep going like that. And then there's also a formula for these coefficients. The formula is Cn equals the nth derivative of f evaluated at x equals a divided by n factorial. And I'm pretty sure you guys want to know what factorials are. N factorial is just the product n times n minus 1 times n minus 2, and so on, all the way down to 1. These things grow pretty quickly. Anyway, so that's the formula. And that's what's known as a Taylor series. And Taylor series, like I said, are very nice because I'm not going to do it here, but they give you a very useful way of approximating any analytic function. As long as you know all the derivatives and um, you can evaluate this thing at any point in the domain as long as it converges. It doesn't converge for every value of a necessarily. There's what's called a radius of convergence of the Taylor series. But as long as you're within the radius of convergence, then this Taylor series does converge, and a matter of fact, it converges to f of x. So anyway, and another thing I should mention is that the most common value of a that's used is a equals 0. And when we're spanning Taylor series about x equals 0, it has another name. It's called a Maclaurin series. I think Maclaurin lived around the same time as Taylor, and I think he discovered this series independently of Taylor. But the Taylor series is more general. So anyway, um, but how do we prove this? I want to give you kind of an outline of a proof of Taylor's theorem. So how can we prove these formulas I wrote down on this first slide? Well, it's not that hard actually. I mean, what we do is we just keep differentiating this equation 1. And then when we do that, if we keep differentiating as many times as possible, we end up with formulas for the coefficients. So let's just kind of see how this works. This is kind of an outline of a proof. I mean, you'd have to fill in some of the details to make this a rigorous proof, but let's first evaluate C0. Well, that's pretty easy. I mean, if you look at the form of the this equation here, f of x equals c0 plus c1 times x minus a, and so on. When we're evaluating at x equals a, notice that all the terms are going to be 0 except for the leading one, c0. So that gives us f of a equals c0. That's the first equation in 2. And if you want to get the second equation, you want to find c1, all you have to do is differentiate. I guess that's what I'm doing by what I'm calling equation 2. It really should be equation 3. But when we take the derivative of this formula, equation 1, we get f prime of x, and then the c0 is going to disappear because the derivative of constants is 0. But then the derivative of x minus a is 1, so we're going to get c1. And then when we differentiate x minus a squared, you get 2 times x minus a. So you're going to get 2c2 times x minus a. And I mean, I do it here. So what you'll end up with is c1 plus 2c2 times x minus a plus 3c3 times x minus a quantity squared, and so on. And now again, we're going to plug in the value of x equals a, and every term except the first is going to go to 0 because all the terms x minus a to the nth power are going to be 0, and we're just left with c1. So we conclude that f prime of a is c1. That is the second equation in 2. C1 is f, just the derivative of f evaluated at x equals a divided by 1 factorial, but 1 factorial is 1. So we just get f prime of a in that case. And it lets us do one more example. What about the second derivative? Well, now we can take one more derivative. And if we do that, we get 2c2. That's going to be the constant term now. Plus, and then if you keep doing this, you're going to get 6c3 times x minus a. These things get kind of complicated. And you can keep going if you want. That shouldn't be a 3. I think that should be a 12. Yeah, but anyway, the important term here is f double prime of a, and again, all the terms are going to cancel except the leading one, which is 2c2. So now we can divide that by 2. We get c2 equals f double prime of a divided by 2. But 2 is the same as 2 factorial. And if you keep going like this, you'll find that Cn is the nth derivative of x evaluated at x equals a divided by n factorial. That's how you prove. That's how you prove Taylor's theorem, the form of the Taylor's theorem. So that's a very, very nice theorem. And here's some examples. These are common Taylor series. These happen to all be Maclaurin series as well. Like I said, Maclaurin series is the most common form of Taylor series. So here's some ones you'll see a lot. I'm actually going to derive the first 3 of these. So e to the x has a very nice form. E to the x is 1 plus x squared over 2 factorial plus x3 over 3 factorial plus x4 over 4 factorial, so on. You can write that as an infinite sum n going from 0 to infinity of x to the n over n factorial. That's how it's usually written. And sine and cosine also have some pretty simple forms. In the case of sine, sine's an odd function. And what that means is the only powers of x in the Maclaurin series are going to be the odd powers. And it looks almost like the form of e to the x, except the sign SIGN of the terms alternate. And like I said, you only get the odd terms, but you always get the same factorial in the denominator as the power, just like you do for e to the x. And similarly for cosine. Cosine's an even function, but now that means we're only going to get even powers of x. And it's the same idea as a sine. Again, the SIGN of the terms alternate like they do for sine, and we only get the even powers. And there's a couple more here that I'm not going to derive, but they have very simple forms. The natural logarithm of 1 plus x has a nice form. X minus x squared over 2 plus x squared over x cubed over 3 minus x to the fourth over 4. Notice there's no factorials in this formula. And this one doesn't converge for every value of x. I mean, the radius convergence of this Taylor series happens to be 1. That means that this Taylor series really only converges when the absolute value of x is less than 1. And then similarly, arctangent has kind of a similar form. It's just since arctangent's an odd function, you only get odd powers, but it looks kind of like the Taylor series of natural log of 1 plus x. The signs, SIGN, of the terms alternate like they do for natural log of 1 plus x, but here you only get the odd powers. Otherwise, it has basically the same form. And once again, the radius of convergence is just 1. So this series only works when the absolute value of x is less than 1. Um, anyway, that's some common Taylor series or common Maclaurin series, if you like. And now I want to do some examples of how to compute them. So how do we get this first formula here? The formula for the Taylor series of e to the x. It's actually pretty simple. I mean, you know that the derivative of e to the x is e to the x. E to the x is equal to its own derivative. And since it's its own derivative, it's also its own second derivative, its own third derivative, its own nth derivative in general. Doesn't matter how many times you differentiate e to the x, you always get back e to the x. And that's nice because that means we know all the infinitely many derivatives of e to the x. They're all just e to the x. And if we want the Taylor series about x equals 0, which is just the Maclaurin series, we just let a equals 0, e to the 0 is 1. So all the derivatives evaluated at x equals 0 are equal to 1. Well, that's pretty nice. That means that Cn is going to be just 1 over n factorial, right? Because the the nth derivative f evaluated at 0 is 1, and then we're always dividing by n factorial. So we got e to the x is a sum as n goes from 0 to infinity of x to the n over n factorial, which if you like, you can write term by term. You get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And a nice special case of this formula, you can plug in x equals 1, and that gives you a very rapidly converging series for e. You get 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, so on. It's just an infinite sum as n goes from 0 to infinity of 1 over n factorial. Like I said, factorials grow very fast. That's why you don't need very many terms in this series to get a good approximation of E. As a matter of fact, if you just took the first 10 terms, you would get an approximation of E that's accurate to 6 decimal places. Pretty amazing. And that's probably the easiest example I can think of. Sine and cosine are a little bit trickier, but not too much. So sine, you probably know the derivative of sine is cosine, and derivative of cosine is negative sine, and then you can go a couple more. The derivative of negative sine is negative cosine. That's the second, yeah. So the second derivative of sine is negative sine. Third derivative is negative cosine. Fourth derivative gives you back to sine. So when you keep differentiating sine, it has a period of 4. So that means you can write this in kind of a general way. You can say that f4m, I'm calling it m now. So the 4mth derivative of sine x is always sine x. And the 4m plus first derivative is cosine x. 4m plus second derivative is minus sine x. And the 4m plus third derivative is minus cosine x. But we want to evaluate these things at x equals 0. Well, that's easy. Sine of 0 is 0. So the 4m derivative of sine x evaluated at x equals 0 is 0. The 4m plus first derivative evaluated at 0 is 1. Cosine of 0 is 1. The 4m plus second derivative evaluated at 0 is again 0. And the 4m plus third derivative evaluated at 0 is negative 1. And you kind of see the pattern here. We can write this a little bit more simply. We don't have to use m, we can use n. We can just say this 2nth derivative of 0 is 0. Every even number of derivatives of sine x evaluated at x equals 0 gives you 0. And every odd number, 2n plus 1, the 2n plus first derivative is 0, gives you minus 1 to the n. So when you put all this together and calculating the Taylor series of sine x, I mean, we're going to get Cn. So C2n is 0. All the even terms have coefficients 0. That shouldn't be a surprise because sine is an odd function. So we shouldn't get any even terms. And the 2n plus first term turns out to be minus 1 over n, minus 1 to the n over 2n plus 1 quantity factorial. Um, and so when we put all this together, we get this nice form of Taylor series of sine x. Sine x is a sum as n goes from 0 to infinity of minus 1 to the n over 2n plus 1 quantity factorial times x to the 2n plus 1. If you like, you can write that out term by term. We did it a couple slides ago. Just looks like that. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7 over 7, so on. So anyway, that's how you do this. Sine and cosine is very similar. Basically the same idea. We again notice that the derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is sine, derivative of sine gives you back cosine. Again, you have a period of 4. It's just that you're starting with cosine instead of sine. And when you evaluate everything at 0, this time only the even terms are going to give you something that's non-zero. So you're going to get the 4m derivative evaluated as 0 is 1 this time. 4m plus first derivative evaluated as 0 is 0. 4m plus second derivative evaluated as 0 is 1. Yeah, that should be minus 1, I think. And then the 4m plus third derivative evaluated as 0 is 0 again. So again, you can write this a little bit more simply if we write in terms of 2n. The 2nth derivative evaluated as 0 is minus 1 to the n, and the 2n plus first derivative value is 0, 0. So this time we're only going to get terms with even index. And you can calculate Cn. Cn in this case is just minus, C2n is minus 1 to the n over 2n quantity factorial. And C2n plus 1 is 0. This will give you the form I wrote down here for the Taylor series of cosine x. Sum as n goes from 0 to infinity, a minus 1 over to the n over 2n quantity factorial times x to the power 2n. And if you do this term by term, you get what I showed on this slide here. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial and so on. And anyway, that's as much as I'm going to do. You can derive the other two Taylor series on this slide if you want. They're a little bit more complicated, but they're not too bad. Just the same idea. And anyway, that concludes my video for today. So thank you for watching. Long live math, and I'll see you guys next time.